So let me first give a short introduction to the history of the incoherent alpha effect. So all of us have done simulations and measured alpha effects from test field methods. We know that the alpha effect fluctuates a lot. So there is always a mean part and a strong fluctuating part. So that in that way, we always know that the incoherent alpha effect exists. But in most simulations, we also use a helical forcing. So that gives us also a coherent part of alpha effect, which is either positive or negative. And most of the time we think that the dynamo that has developed is an effect of this coherent alpha effect. And with that there may be shear. So in that case it will be alpha omega dynamo. If there is not a shear, then it will actually be an alpha square dynamo. So now the question is it possible for the incoherent alpha to give rise to a dynamo by itself when the mean value of alpha is actually 0? So that's what we are interested at the moment. So the answer to this question is actually, in a sense, we know that the answer is yes. Because there is this old paper by Axel, Matthias, Petri and Karl-Heinz, where they did simulations where there was a uniform shear and a forcing which was non-helical, and they found that it actually gives rise to a dynamo. And the mechanism there, the fact that such a dynamo might exist was known, because it was thought that the effect of shear is the one that actually gives rise to such a dynamo. And there were two competing mechanisms that were suggested. One was the incoherent alpha effect, and the other was what is known as the shear current effect. So let's say, let's just write down the mean field equations to begin with. So this is just taken from Axel and Matthias's paper. So this paper that will come quite often in the discussion today is Brandenburg, Radler, Reinhardt and Kapila, and that will be called BRRK.
Which year?
Which year?
2008, no?
2008.
2008.
And I always confuse it now, but there's another paper which is BKKR. Where's what?
Brandenburg, Corpi, Capula, and someone?
No, that is Kemel and Kleorin and Rogachevsky. Completely different.
2008 Astrophysical Journal. Okay.
Comment to both.
And there were actually another series of papers by Tarek Yusuf and Alexander Shekotihin, Tobias Heinemann, and few others. I think one of them is Mac Williams, and there may be several others. And this was in Physical Review Letters. I'm forgetting. Yes, that's also 2008. And they also found that it's possible to have a dynamo which has non-helical forcing and a shear. So all these simulations were done with uniform shear. They were done in the shearing coordinate frames. Okay. So that's basically we always try to understand dynamos, the large scale dynamos in terms of mean field models. So let's just first write down the
2008 we shouldn't forget, of course. 2005 we shouldn't forget.
Yes, actually there is also Brandenburg 2005, which is a paper we know for the near surface shear layer, but that's also a paper where there is exactly the same results. But of course, it was not yet measured by test field methods.
No, but it was that was one of the reasons to develop it actually. There was this was all at the same time when Günter Rüdiger already and Karl-Heinz Redler had the results with Stepanov in that case that the alpha that the shear current effect should not work. And that agreed with my other 2005 paper of that same year.
Right.
And so under this, and then the suggestion that Günther made was it could be because of the fact that the contours of shear are more complicated, inclined. And that was then the reason why I developed the test field method, first in 2 dimensions. And only afterwards we did the 1-dimensional test field method. That is now mostly in use.
Yes. So, just to get back to it, let's write down the mean field equations. So the mean field equations are minus alpha x j bj, where j can be y or x, and then minus actually in this model the derivatives are always with respect to z, because see we have already averaged about the, okay, so let's see how we come to the mean field equations.
So why is there a partial derivative on the right hand side there?
Why it's not what?
Right, not.
Oh right, so it's a curl up, yes.
Yes, so typically we write the equations for A,
Yes.
and when we keep writing them, we keep forgetting that the B will have a derivative then. It happens to me all the time.
But then should be alpha y j, no?
Yes.
Yes, you are right. Yes. Yes, exactly. Yes. Okay. So we arrived at this mean, I don't need to tell anyone how we arrived at the mean field equation. Everyone here knows how to arrive at that. But we have already averaged over x and y, and things are only a function of z now. And then I am writing the mean field equations. So this is alpha yj, and then I have minus eta yx del z square of by plus eta yy del z square of bx. Okay. And then in this one,
Does eta contain both the turbulence and the molecular?
Forget about turbulence.
to
Forget
begin
about
with,
molecular.
yes, but let's forget the molecular for the time being.
Forget about molecular.
Yes. And then I have plus alpha x j.
The etas will be not considered incoherent in this paper, and they are diagonal.
But in 2008 paper they were considered.
Yeah, I know. But that was not found to be important, right?
No. True. It's not essential for the dynamo.
Right. So these are the mean field equations. So there are 2 ways really by which it can be a dynamo. One of them is an interaction between shear and alpha, but we know that the mean of alpha is 0. So for the moment, if we think about the mean, alpha doesn't play a role. But then there is another interaction which is by the shear current effect, which is basically given by the component eta yx. And this is the one that was measured by BRRK by the test field method. And we have attempted to see how this one varies as a function of shear. It turned out that they came up with values, but there were quite large error bars. The error bars almost included 0. Now, according to this, the shear current effect, the eta yx has to satisfy 2 things. It has to be non-zero, and it has to have the other sign as a shear. None of this were really confirmed by the simulations of BRRK. So that gives the situation that we need to now consider other possible choices. Meanwhile, these people, the Shikochi, Heinemann and Tarek Yusuf, they looked at this dynamo and they actually looked only at the growing phase of the dynamo. And then what they found out was that the growth rate of the dynamo is actually proportional to the shear, and then the mode at which the dynamo develops, let's call it K peak, actually goes as square root of shear. Now this was not something that was given by the midfield models. Also, if we assume that shear current effect is working, but at the same time assume that the eta in the shear current effect varies linearly with shear, then we actually do not get this scaling. Then BRRK themselves actually show that gamma actually goes as S to the 2. So in some sense, the scaling seen here is possibly not from the shear current effect. Possibly not, because we don't really know how the eta for the shear current effect depends on S. But however, the situation is basically this. So then came the recent paper by Tobias Heinemann and McWilliams and Shekochihin, which was a paper which was actually submitted in 2008, somewhat after their earlier paper, and with lot more authors. I think our friends Chloe Severin and Legojevsky were also 2 more authors in this list. But somehow the author list has dropped off. The conclusion has changed somewhat. And now it turned out there are 3 important.
Accepted or
It's still under consideration, but I think it has more chance of being accepted now.
It may not even have been submitted back then, was it?
When we saw it in the archive,
It was only in the archive, maybe. I don't
oh, I
know.
see. It was not submitted in 2008.
No, I'm not sure now. I would not
I see.
be sure.
So, however, it was in the archive. And there are a few points that are made by these people, which turns out to be quite interesting. One of the things they say is that there is no mean growth of the field. So if you, in the simulations, for example, or in this, okay, so this is a purely theoretical work. And what they're considering here is actually a velocity field which is being forced just in simulations, but they're assuming that the Reynolds number is close to 1, actually less than 1. So they are completely dropping off the nonlinear term in the Navier-Stokes equation. So in that case, it is just diffusion equation. And velocity one can just obtain from the forcing. The forcing is delta correlated, so they can exactly find out what the velocity is. They can put that in the induction equation and then average over the forcing. So the average magnetic field, which is now averaged over the forcing, their point is that this one does not grow. And this they found out. So the way they do this problem is actually by expanding their correlation functions in Kubo numbers. So let me not go into technicalities here. But the point is this result seems to be true in all orders. So irrespective of the perturbation series, that's what their claim is. And then what they found out is although that doesn't grow, this one does grow. And they said, let's say this grows as e to the power twice gamma t.
Don't forget the overpass.
Yes, but for them it's not sure exactly where the overbars are and where they are not. Because for them it is not.
Eventually it does become for them important, because is this the moment that you're doing in equation alpha,
Yes.
you are working with average equations.
Yes,
These are
but
horizontal
then-
averages, and this average, of course, is over realizations.
That is true, but they are not immediately. It's not immediately obvious that they are actually doing that. They may be doing both the averages in the same go. Because you see, for them, alpha is actually something like u dot curl u, and then this u is some Green's function over the force, and dot curl over some other Green's function over the force, same Green's function, but, and then they're actually, this averaging is done over the noise. So that's kind of the alpha they have. Possibly, that's what I remember. So,
But after this averaging, the alpha is still fluctuating or not?
no, after this averaging there is only one alpha, but I think all the averaging in their thing is done in one go. I'm not very sure at the moment, I can look it up. But I think they don't make a distinction between the two averagings as clearly as we do. I think. Okay, so the claim is that this one grows, with a growth rate gamma, and then this gamma actually satisfies this one. So gamma grows as shear rate, and the peak goes as s to the power half. So, and then that actually gives the same, I mean, they basically reproduce the numerical results of their earlier paper, which is quite nice. So, then we thought that it may be that there is an even simpler model in some sense, where we can reproduce the same results, which is to take these equations and then take alpha here to be having zero mean but fluctuations. So let's say we take alpha ij, whose mean is 0, and then we assume that alpha is Gaussian, because practically no analytics can be done if alpha is not Gaussian. Also, BRRK had actually studied it and actually looked at the probability distribution of alpha, and then that fits the Gaussian pretty well. So there is good justification for assuming alpha to be Gaussian. The next assumption is the one that is crucial and the most strongest, where we assume that alpha is actually delta correlated in time. We also assume that different components of alpha are completely decorrelated. So alpha is basically a 2x2 matrix, and as we progress in time, this component is completely decorrelated with this one or this one or this one. So in some sense, this correlation function is fully diagonal, and then let's call this Dij. So that's the idea. Now the question is, using such a noise, we would try to write an equation which are the same equation but now averaged over the noise. Now there is a nice technique that actually allows you to do that.
So under which conditions would we have a rank 4 tensor? None, right? Yes. If there is a delta, of course, then never.
Yes.
Right.
But we can change this, of course.
Mm.
And we can still do the same formalism. It just gets more messy. This is a more stricter assumption. If we get out of this, then our whole analytics falls down. But if these are kind of relaxed, we can still do the same analytics, but with more messier terms appearing in the equations.
But both of the assumptions, so delta correlated in time and correlation only on the same elements,
Yes.
are not supported by the simulations of this paper of 2008.
I don't know about the delta correlation.
The Gaussian is confirmed there, but
Yes.
the other assumptions are ready to be added.
Yes, other assumptions were not
But
checked.
we didn't check them carefully in that paper, no. But we checked them afterwards.
Of course, it will never be truly delta correlated.
And they were not well correlated at all.
But it will never be truly delta correlated. But we can kind of think that if our theory applies for large times compared to the correlation time of alpha. Kind of. It's never easy to go from a delta correlated limit to a finite correlation. It's always singular. But this is where we can actually do some theory. Okay. Of course, sometimes there is no point of doing a theory which doesn't match with experiments. But, okay. So the thing is, there is this nice thing which is often goes by the name Gaussian integration by parts, which says that the following theorem is true. So let's say nu as a function of t is a Gaussian delta correlated noise. Or actually I don't need to assume delta correlated, it's just Gaussian. And let's say there is some other function which actually depends upon nu. So in the sense of variational calculus, this will be called a functional. So f is a functional of nu. So then the theorem goes as following. So let's take nu at time t f of nu and do an averaging over the statistics of nu. And because nu is Gaussian, the following theorem holds, which is that nu t okay. So what happens is, see, this is an average of products, and that actually separates out. So you have to take the functional derivative of f relative to nu and have the nu correlator. Actually, this is something that Alex, Matthias, and Nicolo and myself had a discussion some time back, where I promised to tell them more about the Kreutzmann model. We did it for one day and we actually never continued. But okay, so this is basically what is known as Gaussian integration by parts. There are several references where this can be found. One of the places is actually Frisch's book, where he actually discusses this. But the way he does this is that he replaces, see, nu here, he basically, you can think about it as the following. Nu in some sense is a function of t, right? So in some sense, nu lives in an infinite dimensional space. You can take 0 to t, and then there are discretizes to n t partitions, and then nu lives in kind of in an infinite dimensional space. But let's say nu lives in a discrete space. Then this problem becomes essentially a problem in calculus of several variables. So it comes down from functional calculus to calculus of several variables, where it becomes simpler. And then that's where Uriel actually does it. And then you can actually show that such a relation actually holds true. So let's say if nu is discrete, and then there is nu j, then this averaging will look like following. So nu j f of and next, if you just assume that j is 1, then it's actually quite easy to prove this theorem.
This was variational derivative?
No, now it's no longer variational derivative, because nu is discrete.
Oh, that's, yeah, nice.
So now nu is discrete, so it just boils down to partial derivatives. And then now if you assume j equal to 1, you can actually prove it quite easily yourself. So that's how Uriel actually does it. And there is the book of Zinjastin who does it in kind of 3 or 4 pages. And yes, okay. So so this is what we are going to use. So you see this one is going to be alpha. And this function which depends on alpha is going to be the magnetic field. So the average of alpha and magnetic field is then going to be separated into a product. And the question comes how to evaluate actually this functional derivative. The other question actually, okay. Slightly sloppy, this will have this. This will have this. Now you see there is an advantage of having a delta correlated nu. Advantage of having a delta correlated nu is that this t prime must be equal to t. So you have nu, so basically you have the nu correlated, but that plays a more important part when you look at the second term. See, in the second term, this functional derivative is now with respect to the same time. So now kind of try to think about it in this way, that this f is the magnetic field. So time derivative of the magnetic field depends on alpha. And it depends on all the alpha that has gone by in history. But it cannot depend on alphas which are going to come in future. It must be causal. Okay. So then this derivative will actually couple you to history all the way back. And then there will be an integral over the history, which is quite messy. But the fact that this is delta correlated shortens the history down to that instant exactly. And that actually gives you quite a simple expression for this functional derivative. But taking that is somewhat tricky, in a sense that, again, you are kind of going to take limits. You are trying to look at this integral, but basically this derivative which depends on all part in history, and then trying to cut it short. The best way to do this, so basically what will appear here are theta functions. Functions which goes by a jump at t equal to t prime. So t prime less than t, it is 0. T equal to t prime, it is 1. So functions like theta function will appear here. So again, one has to take the limits in a proper way. And then the right way to do this is to do it this way. So, but to illustrate the rest, we will go to an even simpler model, which is one of the earliest paper on the incoherent alpha effect, and that is the Vishniak and Brandenburg paper. So in this paper, they actually dealt with an even simpler model. So all factors of k has been dropped off. This has just become a zero-dimensional model. But the idea remains the same. So let's say now we are trying to average this. So I am trying to write an equation for this. This one is of course easy. The trouble comes from this one. And then when we use this Gaussian integration by parts.
Have you done anything? Sorry, no, it's okay.
So I get the alpha correlated. And this one. Okay. So let's now try to evaluate this functional derivative. To do that, we actually finally take the by equation and integrate it. Okay. Now think of these two integrals as essentially sums, and then try to take their derivative. Now of course if you take a derivative with respect to alpha at some earlier time, then alpha at some earlier time has affected bx at some earlier time, which has actually affected this integral. But if it exactly at this time instant, then by cannot depend on alpha. So this derivative is actually 0. Now in a similar way, let's try to evaluate the other one. And here again, so
I think you're done with this.
No, I did it with by.
I mean, you're just showing here that the V average, of course, is 0, which you want to go to the second one soon.
Yes, but I also want to take the other functional derivative,
But it doesn't show up anywhere.
which is this.
Yeah, not in that model.
It doesn't show up now, but it will show up in the second moment.
Yeah. Sure.
Yes, but I was just
Yeah.
completing the calculation.
Okay. Yeah.
So-
Mhm.
So now if you look at this, and again think of it as a sum. So think of this integral as a sum in time, and then both at the same time actually give me just by at exactly that time instant. Okay, so there are only two functional derivatives that I will need, and I actually now have them. So now let's try to write down the average equations. So del T of Bx, which is actually done, is actually average of alpha By, which is this, and that is actually equal to 0. And then what remains is just this one. So this is and this is even easier. So this is S. Right. So from this it is obvious that this model doesn't have a growing mode. If you just look at the matrix, where we say C1 is okay. So we reproduce the fact that the Shikochin found out is that the average B actually doesn't grow. Now, one has to be careful. I mean, we are actually quite explicit in our notations. So we are explicitly saying that there is a double averaging here. The bar actually denotes the averaging over the x and y direction, which gives me the mean field. And then the left and right angles give me actually the averaging over alpha. So once both the averagings are done, this thing cannot develop into a dynamo.
So right now, the B bar X in brackets is the amplitude of one of the K modes in a periodic box. That's functional Z.
No, B bar X is just the total B bar X. You can of course Fourier transform it, but see, this model doesn't have a K at all.
Okay.
This is 0D model. But of course one can put the K's back.
I mean, first of all, you could think of B bar being a horizontal average. And then the important thing is that the angular brackets are not volume averages now, they are realization averages. So you do the simulations with different realizations, different initial conditions, and have a whole distribution of them, and you find that you have a distribution centered around
It's
0.
not quite clear what you're. I mean, if I have a dynamo wave and I'm measuring Bx at a point, then yes, its average under a whole bunch of realizations will be 0, even if there's a growing dynamo wave. Because my bunch of realizations is equivalent to initializing different phases, and as I average over phases, I get 0.
You are just thinking about a random phase.
So if I think about a dynamo wave, if I averaging over a Z is equivalent to averaging over phase, and this language right here, averaging over realizations should be averaging over phases as well as everything else.
Yes, maybe that should be checked. I mean, that's true what you say. So if you have any dynamo in a periodic domain, right, I get all kinds of realizations, they all shifted, and of course they all average to 0. So it's probably true, and you just need to do a corresponding analysis along the same lines. I mean, normally one doesn't actually do such an analysis.
That's why. We talked with him very briefly about this yesterday, and I've been sort of confused about what does averaging speeds mean. So, that's all. And it gets very hard to actually.
I mean, actually, what we really want to think of in the end is a random walk thing. So we have, I mean, how do you do this? So you do a random walk, and of course you find something which goes like this.
Yes.
Then later on it goes like this, and then it goes down again, right?
Yes.
It just has larger and larger.
It's like an oscillation with growing amplitude
Yeah.
in some sense, but not a periodic oscillation, but a random one. But that the average is not growing does not mean that there is no dynamo.
Yes.
It's somehow misleading to connect that, because such a signal would be attributed to a dynamo, of course, although the average is, the simple average is 0.
Yes,
Yeah, right, that's true.
In analogy with random walk, you could say that one could have a random walk with an external constant force. Then your zero base will no longer remain, but the zero base will keep on increasing with time. In that case, you will have a random walk which goes like this.
Yeah.
And the other one is, of course, that there is no external field, and it goes like this. So,
I see.
so we're basically saying that
Yes.
this model is like a dynamo, it's like a Brownian walk with no external field, and it just the mean is 0, but of course it fluctuates, and the fluctuations increase with time.
So it's still a dynamo.
It's still a dynamo.
It can be a dynamo, at least.
In principle, yes. We haven't seen the second moment yet. Now if we look at the second moment, and now there are actually 3 of them. So we have bx square, by square, and now let us try to write an equation for each one of them. So now I'm not doing the eta terms because we know they are simple. So the interesting thing here is bx, and then the del t of bx gives me an alpha by term plus other terms. And then this one is again the alpha correlated. Okay, now one of them is 0, the other one is no. Right. So this one gives me okay. So you see this gives rise to a term which is actually off diagonal. So the evolution of bx square is actually now related to by square. So if we now proceed in this way, we actually get the following matrix. So let's say del t of C2, and then N2 takes the following form. So where D is actually the alpha correlated. Now this matrix again can be diagonalized, or one can actually look for the characteristic equation of this matrix, and that will give us the going modes. So if we actually find out the characteristic equation of this matrix, that turns out to be something which is not too bad. So it turns out that this is
quite unusual in terms of dynamo theory, cubic of this form. And that's why we never saw anything like this with the.
So yes, that is actually quite unusual in dynamo theory. See, there's the solution of a cubic equation. Typically, what one would have thought that, okay, so what would that give? That would give me that gamma is minus eta plus 4ds square to the 1/3. Of course, what we have here is cube root of 1. So that will be 1 omega square. But let's not worry about omega and omega square, because they both of them have real part which is negative. So let's worry about only one. So first thing is that gamma actually is proportional to s to the 2/3, which is of course not the same result as s to the 1. Now one can actually recover that by now replacing all the k factors here. You see the etas will have a k factor with them. This is k square, k square, k square. S of course doesn't have a k factor. And if you look at D, D is the alpha-alpha correlator. Each alpha will come with an ik. So that will give me another k square term. So there is a k square here. Once I put that back here, then I get an equation which is actually somewhat different from this one by just the k factors. So this is okay. So
shouldn't the sign of D change, or the entry in the matrix where alpha
you mean ik gives
gives a minus, no?
yeah, eventually it doesn't. Because actually it's
Unless you-
actually in this model I didn't put ik, I just put k. But I can go back and do it for the more complicated model that I wrote down.
But for the moment, assume that it means simply to invert the sign of D. What consequences would it have?
D must be positive definite.
Yeah, because of that sign, I mean.
So if it changes sign, then of course things will be somewhat different. Because then it will be -1,
Yeah.
minus omega and minus omega square.
But I think it really doesn't matter because you have an incoherent alpha effect. So the signs of, and we are only talking about the ik in front of alpha, and alpha has an indeterminate sign. Therefore,
Yeah, but not
doesn't show up.
alpha correlated, average.
Yes.
This has a determined sign.
No, I think the sign is important, but not so important. Okay, but I'll come back to it. Just this one is actually calculated from the full model.
Why do you have two factors of D?
Right. So this one is calculated for the full model. Where see, I have two changes from the full model. One is that alpha appears in only bx equation, not in the by. In the full model there are two alphas.
Oh,
So there is a possibility of an fluctuating alpha square dynamo also.
Yeah.
So this equation comes by putting all of them together.
And the I factor?
And the I factor.
Okay.
So I factor and putting everything together, this is the one that appears. Okay. Now the good thing about this is, let's say for the time being we are looking for large S, and then we can drop the next term. And then we have an equation which is gamma plus eta k square whole cube is 4k square dyy s square. This is actually exactly the same equation that is obtained by Shikuchi in their paper. So the dispersion relation that we obtain is exactly the same, and from that we actually get exactly the same growth rate. So in some sense, the 2/3 growth in the zero-dimensional model is actually equivalent to gamma going proportional to S in the space-time dependent model. So far so good.
So gamma is proportional to S for this K. This
Yes.
particular K.
No, for this K dependent model.
Yes, but that.
Oh, yeah, exactly. I see what it means. So if I actually plot this dispersion relation gamma as a function of K,
Then you have a peak.
it looks something like this, where this is actually K to the 2/3, and this is actually K square, and then there is this peak, and which here, this peak is the one that grows as square root of S, and the peak, the gamma at the peak goes as S. So in some sense, this is gamma peak.
Yeah. And the D is not depending on S, no?
No, D is not assumed to depend on S. So D is assumed to be a constant. Okay. But there is also the possibility in the more complicated model, the possibility exists of actually having an alpha squared dynamo. And which is then a product of dyy and dxx. And the dispersion relation for such a dynamo is just like this. Of course, it could be also this, depending on whether eta is greater than or less than . So this branch is when eta is greater than them, and this branch is for when eta is less than. Okay, fine. Now, so we have reproduced all that Shikochihin has seen. Actually, Vishniak and Brandenburg have also seen this 2/3 growth, and their technique was somewhat different, but quite beautiful. So instead of doing this one, what they did is, they looked at Bx by By. Now if you take this equation, the Vishniak and Brandenburg equation, and look at Bx by By, then the equation for Bx by By actually becomes an equation for a Lagrange equation, but with an additive forcing. So you can even interpret this equation as a Lagrange equation, but with a multiplicative noise, which are difficult to deal with. Whereas Vishniak and Brandenburg could actually map this into a Lagrange equation, but with an additive noise. From that, they could immediately write down the Fokker-Planck equation. So the Fokker-Planck equation basically is telling you how the probability distribution of Bx by By is working. See, what we are calculating here, these quantities, are actually different moments of that probability distribution. Where we are doing with moments, they actually in some sense gone back to the full PDF. And that was a one-dimensional problem where the Fokker-Planck equation could actually be solved. So they could solve the Fokker-Planck equation and from that find out exactly how things grow. And their conclusion were also exactly the same, that the mean value of the magnetic field averaged over alpha does not grow, but it's the mean square that grows, and it grows as s to the power 2/3, which is exactly what we obtain here. Okay, now there is something more beautiful in this, which is now you can be nasty to yourself and say, I want to calculate even higher moments. So I am not only happy calculating C2, I want to calculate C3 and C4. So as I go to higher order, of course, things get more nastier. For example, if I want to calculate C3, I will have something like Bx cube, and then Bx square By, Bx square By square, this is becoming nicely masochistic.
The central one is to be
Sorry?
dropped. The central one is to be dropped.
All right, let me see.
It's on the
All
floor.
right. That will also appear in the next order. So then one can write down and then one can again find out what are the eigenvalues of N3. So now let us look at things somewhat more in a general sense. So let's say C1 goes as e to the gamma 1 t, but just to, and then C2 goes as gamma 2 and so on. But just to make life slightly more simpler, we will call them not gamma 1, gamma 2, but somewhat using the same notation as Shikochigin. I will call this one e to the power gamma 1t, call this one e to the power twice gamma 2t, and then for C3 it will be e to the power thrice gamma 3t, and for C4 is e to the power 4 gamma 4t. But the trivial dependence on, so let me call this pth order. The trivial dependence on gamma p on p is the linear one, and that is actually already taken into account in this. Now there are two more interesting things that comes out of this. One is if you actually look at N3 and look at its characteristic equations, the characteristic equation of N3, where is that? Maybe I didn't write it down.
It's in the appendix.
No. The matrices are, but not the.
Oh, the characteristic.
But anyway, it doesn't matter so much. Yes, so what happens essentially is something quite interesting. See, N3 satisfies a matrix N2. N3 is actually a 4 by 4 matrix. So the characteristic equation will of course be a fourth order equation. Now interestingly, it turns out to be an equation to be this. So you see, one of the roots is 0. So effectively, we have to again solve a cubic equation. The only difference is this 4 has now become 18. But the beauty of the thing is, in some sense, the cubic is central to the problem. See, I would have thought that in third order, I would have to solve actually a fourth order equation. But it turns out really one has to solve a cubic equation. So if you now kind of try to solve this, how the structure of the roots of this equation change in the complex plane. So for example, if you plot the complex gamma p's, then gamma 1 is actually minus eta. So let's say that's here. And then gamma 2 is 1 omega omega square. So you actually have something like, well, this should be more than this. And then when you go to the next order, you actually get terms which are along these lines, but not exactly the same, because it is not 18 but 4. So maybe, and one additional thing which actually drops just on that, because this equal to 0 means the growth rate is actually minus eta. If you go to one order higher, to N4, then you will actually get things like this. The structure is quite interesting. And then the additional root will actually come and fall on this. Now there are 2 of them, because this is 3 and there is 2 more which makes 5. The 2 extra roots will fall on this. Okay. So somehow the cubic is central to the problem. That is one thing. Second is, now let us plot this, look at this gamma piece. So gamma 1 is 1, gamma 2 is, or rather twice gamma 2, twice gamma 2 is minus twice eta plus 4 d actually this right there. Okay. And now okay. So basically now let us divide 2 by 2 and 3 by 3 and let's just divide by 2 on both sides, in each of them. So then this one goes off and over here I have 8. Then this one goes off and over here I have 27. And this one and over here I have 64. So I can take gamma p and then I can add that to it eta, divide by ds square, this is all square. To the 1/3, and then I have 1 by n to the power p, and then something here which depends on p. So if actually, now let us think, how would we expect the gammas to behave? Now of course we are looking at the probability distribution of p, probability distribution of b. So if the probability distribution of b had been Gaussian, then various moments will actually be linear with each other. So let's say we completely drop these terms. If we drop these terms, then gamma p actually is going, in some sense, going linear with p, in other sense is constant with p. Depends on how we define it. We can take the trivial linear behavior away, and so this quantity is actually showing the non-Gaussianity of the PDF of B. And then if we plot this for the 4 numbers that we have, 1, 2, 3, 4. For 1, this is obviously 0. For 2, this is 18 by 27 to the 1/3, and all those kind of strange numbers, and it does something like this. And then I kind of, okay, now we are completely in the regime of conjectures. So we say, let's say this one, let's call this zeta p. And let's say as p going to infinity, zeta p becomes finite. If it is finite, then the one on the top must be a cubic polynomial in P. So I can choose an arbitrary cubic polynomial, use these 4 values to fit it, and of course 4 values in a cubic polynomial determines it completely, and I get a general expression for this, which goes something like this.
So you could really just do the 5th term, right, and check?
Yes. In principle, yes. So that's the other part of the story. But what it actually says, qualitatively at least, is that this is certainly intermittent. So we have actually found intermittency in quite a simple model. But the determining factor, the one that actually gives intermittency in this model, is the fact that it actually has multiplicative noise. So one of the messages that is kind of now well understood is that if you have a multiplicative noise in a problem, then for a Gaussian noise, you can get non-Gaussian PDFs. And that's exactly what we are seeing now. And this is what has been seen in Triton model, for example. Okay. Yes.
Okay, thank you.
But what about the DNS trying this alpha square diamond? Do you think it's possible?
The fluctuating alpha square?
Mm-hmm.
Yeah, when I looked at the kind of typical DNS values that we have, then eta turns out to be actually greater than dxx dyy square root. So kind of you can take eta is 1/3 URMS by kf, and dxs equal to dxy dyy is 1/3 URMS. And then for any kf greater than 1, you get that eta is actually greater than this.
So what do you mean? These two are different? Are not different?
No, they are same. But if you put kind of dxx equal to dyy is 1/3 URMS, and eta equal to eta t is 1/3 URMS by kf, then actually you get the lower branches actually. So you don't get a fluctuating alpha square dynamo for this. Also, such a dynamo peaks at high K. See if you look at the dispersion relation, it peaks at high K.
But is there a reason to make this assumption for D from SOCA? What you have said is motivated by SOCA, isn't it?
No, D is not.
What was your estimate for D? What did it just say?
D is just alpha square.
Yeah, but I mean, you have made an estimate for it.
Yes, because I know alpha is URMS 130.
And this is coming from SOCA.
That's coming from
And this has nothing to do with the fluctuations. So
That is true.
it can be completely different.
That is true. That's perfectly correct.
Yeah.
But that's the only thing I had in a way.
Okay. So there is hope that this dynamo might exist.
Yes.
Is there a time period in the dynamo?
That's interesting. No. Because you see, if you the thing is 1 omega omega square, right? So the only thing that has a positive growing part is 1, which doesn't have an imaginary part. So this dynamo doesn't oscillate. If it had been minus 1 minus omega square.
No, it doesn't make sense. I mean, you are only asking whether the B squared oscillates.
Yes. But even if you look at higher ones, the structure of the poles are the same. Because it's always a cubic.
We do, of course, have reversals. And
The B square cannot.
what?
The B square cannot have reversals.
Yes.
So in some sense,
But if you do have reversals, and we always found them as a characteristic.
So this cube one would have reversals, right? No, this dx cube. This
Q.
no, because see the structure of the roots are the same, right? So the largest growing mode. See, if instead of this, if it had been a mode like this, then you would have an imaginary part, and that part will oscillate, right? But the trouble is, this is completely along the real axis. But again, that might change. Such things might change when you go from the delta correlated noise to real noises.
Or if there's a dxy and dyx.
Yes, no, they don't play a role here. Because in this model there is dxy and
It's
dyx.
included.
Yes, but they don't come here.
They don't come.
Actually, they do come. In N2, for example,
Yeah.
so N2, see the diagonal terms are something like minus thrice eta, minus twice eta, minus twice eta, and then minus twice eta, minus dx. So dxy and dyx, in some sense, increase the effective turbulent diffusivity. It's the dxx and dyy which are the off-diagonal terms, at least in second order. If you think in first order, actually, this is minus eta so again they actually increase effective diffusivity, but in first order. It's exactly this term which compares to give different things in the second order. Let me check, I may be wrong. No, I'm wrong. The off-diagonal correlations of alpha always actually increase diffusivity.
And so do the diagonal ones.
The diagonal ones don't even appear in N1.
Yeah.
Again, these are all,
Yeah.
see, these are all, I think, some of these features are artifacts of the delta correlation. For example, I think with non-delta correlated, the other terms will, in N1, the dxx and dyy will also appear. So also the fact that, kind of see, when things are exactly on a real line, such things are often, they may not be stable when you go from delta correlated to non-delta correlated noise. they might change. But there is actually some hope of calculating things in the non-delta correlated case, using something called the telegraph noise. As I was telling Axel, I told Piali and Alex also a little while, actually yesterday. That maybe we can talk about later, maybe, once we write that paper.
Yeah, you were asking about DNS, but you actually mean DNS of the average equations or the...
Or the mean field equations.
No, DNS.
What we do have is, we do have the DNS of pure
not
Cephalon.
DNS, but simulation of the mean field equation.
The simulation of the mean field equation should be possible, right?
Yeah, that's what I've already done.
Yes.
I've done so, this works. But of course with arbitrary values for these fluctuations. But if I drop the shear, it's still there's still a
Yeah, right, yes. And
That's
but
what
that's what we had in our 2008 paper already, right?
No, there was always with shear, which you had included.
Oh, yes. Yeah.
But you can even drop the shear. and it's still
Yeah. No, we have that, and we had that in our appendix for a certain amount
Yes.
of time, and then we dropped it again.
But of course, there's the other sort of DNS, which is more intriguing.
Yes.
To show the real DNS.
Yes.
Yeah, because with the shear it's only non-helical forcing and shear, and you have the you put non-helical forcing and you just leave the ball.
Yes. So in some sense, you see, in that case, the dependence on shear is already known of the growth rate, and we reproduce that. But what is not known is, for example, how the growth rate depends on alpha-alpha correlation. But I don't know how to change the alpha-alpha correlation with DNS.
You said
By changing the crossing wave number. By changing the crossing wave number.
You mean the temporary here, or here?
Yes, the temporal domain.
You want a different distribution?
Not just the strength of it. I mean the D. I want, if I see,
Yes.
I know that this goes as D to the power something. the growth rate. But now if I change D and check that, but I don't know how to change D.
Yes.
Can't you just reset your velocity field?
After a certain while, but how will that change D? That will change the delta correlation to something like exponential correlation, which is already there in a sense that, in a sense, alpha is, in a simulation, alpha will be 3 times the correlation time. Or D will be alpha times the correlation time.
No, but the correlation time would, for instance, depend on the viscosity.
You mean the Reynolds numbers?
Sorry?
You mean Reynolds number essentially?
Yeah.
Yes. No, correlation time depends on
If it-
something like URMS by KF, right?
Yeah, but I mean, if we have a...
But again, that depends on KF, so maybe we can change KF.
I mean, you're still talking delta correlated?
Yeah, well, it will never be delta correlated in...
No, but I mean, if you wanted to change D, then you, of course, I think you just said, you change the amplitude of the forcing.
Yes, so that then you change URMS maybe.
Yeah, and you, of course, can dial yourself into an arc square continuously. And I think that's what was meant.
In the case of the sun, for
And we have such results, but we don't disagree quantitatively by some factor, as you know.
Yes, no, but I was in the full DNS, the gamma is actually...
Yeah.
So it's this dependence that, I mean, this one is already checked by Shekochi and Petu, right?
Right, I see.
But what about this? That's what I'm saying.
Oh, I see. Yes.
And I really don't know how to do that. Because I would think that correlation time, right? And then this will be D times,
But at the moment we are at the level of this line, we are still working with delta correlated in time, alpha.
yes.
So
But-
there's no correlation time issue then.
Yes, but in a simulations, of course, we will not be delta correlated in time.
That's true.
So I kind of, actually this is not this, sorry.
But if we would think as it would be so, then changing D means changing the fluctuation level of alpha simply.
Yes.
And the fluctuation level of alpha should depend on the perfectness of the homogeneous and isotropic forcing. The more perfect it is, desto weaker is the fluctuation level. So it's the higher the forcing wave number, the lower this level should be. Isn't that true? And the lower the forcing wave number, the higher the fluctuation level is. So this way we can influence D. For Kf to infinity, we get a perfect and isotropic and homogeneous turbulence. And alpha will not fluctuate. It will simply have the value
Yes.
0.
Yeah, true. Okay.
And so we can influence it by Kf.
Mm.
Up to
Yes.
certain.
Yes. Right.
Still assuming that there is delta correlation in time.
Mhm.
If not, then we have another issue, which is the correlation time.
Yes.
Okay, so in other words, you say it's proportional to S. Then we also have URMS, and we have KF. Now then you are doomed because gamma and delta S have already the same dimension. So all you want to have is a non-dimensional factor, which you can't make of these two. So
Yes, but you can make it out of Kf by K1 maybe. I think that's what matters.
Yes. Okay, that's all right. And then, yes, that makes perfect sense. So what is D? D then you are saying is related to Kf by K1, right?
Yeah, I would guess so.
Yeah, but it could be another power, of course. So first of all, we know.
Well, we don't know the power, but
First of all, what?
we don't know the power, but there
Yes.
should be a difference.
And it could be minus, maybe even. But I mean, for example,
Hardly, then we should assume that if Kf is growing,
I mean, we
the
know
level of
that-
fluctuations decrease.
we know that D is alpha on S squared times tau, and that is my diffusive tau. It's not a correlation time. Yes, that's correct.
No, it should not have another dimension than alpha squared. No?
No, it has, because there's a delta function in front of this.
Oh, I see.
Yeah, so that's how we have it, and yes, and then this one would be, of course, u to the so alpha itself would be u squared, would be u. So it says for the whole thing as u squared, amazingly. And then tau diff, of course, is the same as u times kf. So it's u over kf. Yes, of course, which is the same as eta t. Which has the same dimension, you know that. Right, and okay, so therefore it's actually it's the minus 1 power.
Yeah. The higher Kf, the smaller D.
Yes. Yeah, like that.
That's what
Yeah,
I
that's
was
right. Yeah, that's good. Interesting.
So you can actually check that.
So I see, yes. Growth rate should be inversely proportional to, that's the fastest growing mode, yes. And of course, underneath, if you don't have the fastest growing mode, it was still underneath the whole thing, right? It was the 2/3.
Yes.
It's still underneath, wasn't it?
Yes.
Yes.
But it's S squared. D is
Yeah,
squared.
I wrote here 2/3 already.
No, then,
And then it's not right, you say? So
yes.
it would be like this?
Yes, S squared to the 1/3.
Uh-huh. Okay. Yes.
So D and S come in slightly different.
Okay, that's 1/3. I see. Then it would be going to the minus 1/3 power. So the growth rate should be depending on kf to k1 to the minus 1/3.
No. That is for if you don't have a k dependence.
That's what I meant.
Yes. But the peak goes as this.
Yeah. Yes. I was actually thinking it's easier to not do the peak, but to do the one for a fixed box size. And
Yes,
actually,
yes.
and actually, we don't even have to look. If we don't have a fixed box size, we don't have a K1 here. So maybe it doesn't make sense to do the unknown, not the other one.
Actually, I had for some time I was trying that if one can write dimensionally what gamma would be. That how gamma would depend on d, and let's say gamma depends on d and s, and you want to write dimensionally what it would be. It's if you assume that gamma is a solution of quadratic equation or a cubic equation or a biquadratic equation, something like that, then you can immediately come up with this pattern. So you need to know three things: gamma depends on d, gamma depends on s, and what kind of matrix gamma is a solution of. I think that's the last thing that was missing from the mean field models. Because you're always thinking it was a solution of a 2 by 2 matrix. That's what is interesting.
Are you sure about this one?
If alpha is big enough, yes. If the fluctuations are big enough, yes. I mean, it's just a question of whether eta is greater than dxx dy by square root or less than.
I see. So that's because the integral alpha and turbulent diffusion come in the same order, right?
Yes.
Yes. Interesting. Yes. Thank you very much, Luba. That was very exciting. So what's then the deal with Monday? Monday we have an ASUPH